this is a transmission line tower, okay, and these are the cross arms. Okay, if it's a single circuit tower, then it will be just like this, and the three phase wires will go. And this if it's a double circuit tower. Okay, there are two circuits, there's one circuit and there's the other circuit. Okay, so but on top of every circuit we have earth wire. Okay, this is earth wire. This is also called shield wire or earth wire. But what is the main criteria for calling a earth wire and earth wire? Earth wire is generally connected from peak of transmission peak to another peak. Okay, like this it's called the earth wire, and it's very thin. Okay, and basically what is to be done is through a copper bond. This is a small copper bond. This is connected to the tower body. Okay, it is connected to the tower body through this material which is called copper bond. Okay, and so whenever a lightning strikes, this is lightning. Whenever a lightning strikes, there are basically two paths. One is this way, I by 2 you can say, and this is say another I by 2. Okay, 2 because it's got two paths. So what will it do? It will, if this copper bond is there, through this earth wire it will and copper bond, it will traverse, and this is the path that it's going to follow through the tower body, and finally it will be earthed. Okay, finally it will be earthed. For all this, it's important that our copper bond are fixed properly, and earthing of the towers is perfect. Okay, earthing of the towers is perfect. Okay, and in the bottom we have our stub, and basically most a portion of the transmission tower is also grounded, but even after that we do this additional earthing where this tower body is connected to earth through there are basically two types of earthing that we follow in power grid, where one is pipe type earthing, which is used where the soil is good, say good alluvial soil, or basically where the soil isn't where soil has got proper soil resistivity, means soil resistivity is low. As we go to the deeper strata of the soil, soil resistivity gets lower and lower, and even those soils where we have moisture in the bottom, that kind of soil. Okay, there we go for pipe type earthing. Pipe type earthing, basically at a distance we dig a pit, and in the pit there is this we fill it with mixture of charcoal and or coke or and salt, and there's this steel pipe that is inserted in the middle. Okay, this is uh, of a specific dia. Okay, this kind of pit we dig, and because the soil is good, that is why it will be earthed properly through this pipe type earthing. Okay, next is counterpoise earthing. Counterpoise earthing, basically where the soil resistivity is on the higher side, which usually happens when the earth is rocky, which usually happens when earth is rocky. Hmm. Then okay, now let's just see what happens if matlab, in spite of these earthing, why we have to face so much say auto reclosure conditions or tripping of lines due to lightning. Okay, first of all, in the bottom we have this bottom of the tower. we have to measure whether our earthing is good or not. And how do we know whether our earthing is good or not? Yes, we can know it using by measuring TFR value. TFR value as per IEEE standard should be less than 10 ohms. Okay, it should be less than 10 ohms. Okay, TFR value should be less than 10 ohms. Okay, then we say our earthing is in good condition. Okay, so basically this is our tower and a cross arm, and this is insulator, and from here our phase wires go. Okay, this basically a suspension tower I have drawn. Okay, this is our insulator. What happens when our earthing is not good? Okay, when our earthing is not good, what will happen is that when lightning strikes, as I have already told, it is lightning strikes, then it can give rise to millions of volts between potential between cloud and ground, and current also I told it could be as mother it can current can be of thousands of amperes. Okay, thousand of amperes. Just in case our lightning yeah, our lightning struck lightning has struck, and anywhere it can strike on the tower or on the earth wire, wherever. And it basically, what the lightning requires is a shortest resistance path to dissipate itself. Okay, it just looks for that. Suppose our earthing is not great, then what will happen is that this tower body through which it's dissipating, through which it is dissipating, it will the voltage will hang on here. Okay, so basically we are not able to ground the excess current that has come into our system through the tower, and our tower so is in high potential condition. Okay, it's in very high potential condition, and because of that it may so happen that the insulation between this insulation across this insulator of ours exceeds the basic insulation level, exceeds its basic insulation level, for which the insulators are designed for every voltage tower. Some insulators are designed to handle these lightning impulses. Okay, uh, so some 765 kV tower, we have 1550 kV. Similarly, 400 kV tower, we have 1050 kV. It may differ also according to the design of insulator. Okay, uh, so hmm, so it may so happen that the voltage that is currently across the tower exceeds exceeds the basic insulation level of the insulator. So what will happen is that this path will get ionized. Okay, which is a very dangerous condition. Okay, this path will get ionized, and normally what should have happened is whatever fault is there in the line or anywhere else, it should get dissipated to earth. But now, because there is this insulator which has already become ionized, so it will behave like a conductor, and the tower is already in such high potential. So now from the tower, current will start flowing to the conductor. Okay, this is also known as back flashover. This condition is also known as back flashover, because flashover is when lightning say struck this conductor, and whatever excessive charges was there, it got dissipated to earth. Okay, but matlab, from conductor to tower body, or from earth wire to tower body, okay, we call that flashover. But now from earth to phase, like that condition has risen, so we call this back flashover. Okay, we call this back flashover. Okay, so now we have discussed what problems can arise due to faulty earthing. Faulty earthing. So it's important that we check that at the tower bottom our earthing is proper. The earthing lugs that we must have fastened at the bottom, it should be ensured that it is in proper condition. And particularly in rocky soils where we do counterpoise earthing, it's important that counterpoise earthing is basically just a 50-meter long wire that we have to install on the ground, and since if you go deeper also, soil resistivity does not improve. So this is basically on the earth surface only, we dig it just barely below the bottom surface. We dig this 50-meter long wire. It's important that this wire is not kept in a coiled condition. If it's in coiled condition, then what happens, this L value increases. L value increases, then omega L, the impedance will increase, and it will unnecessarily increase the resistance, which we actually tend to which we actually plan to reduce. Okay, so our intention is to lower the impedance. Okay, not to increase it. Then next, this copper bond, tightness of this copper bond should be ensured. Okay, and now even after all this, if such conditions like back flashover or say has occurred, then we have our circuit breakers in the power in our substations, and it will lead to tripping of the line. Okay, it will lead to tripping of the line, and it will obviously protect us. Okay, and other things that we can do to protect our system is additional earthing. Apart from this bottom earthing which we have done, we can also do additional earthing, where this from this earth wire at the top, we take one additional wire across the tower and earth it to the ground. Okay, and again at the ground level also we should ensure that our it's proper earthing. Okay, this is an extra wire that we have taken apart from the tower body. This is an additional path, so we call this additional earthing also, or shield earthing also we can say, because this earth wire is also called shield wire. Okay, then and what else, yeah, and in some cases, in some places, we can also install this transmission line LAs. Basically, it is used for specific cases where the terrain is not good. Like I said, in rocky conditions, improving earthing is a big challenge. So what we can do is, because the transmission line passes through several kinds of terrain: hilly areas, plain areas, rocky soil, alluvial soil, various. So we can see, we can earmark particular areas where the earthing is not good. There we can install transmission line LAs. Transmission line LAs basically, if this is our insulator, transmission line LA will be in parallel to this insulator. Okay, it will be in parallel to this insulator, So just like I explained this back flashover case, in this case, instead of routing itself through the insulator and damaging the insulator, it will now travel through the insulator. Basically what we are doing is just diverting our fault. Okay, since LA is in parallel to the insulator, instead of instead of damaging the insulator, the fault will traverse through the lightning arrestor, and it will again travel into the conductor only, but it will travel till the next tower. Okay, say in the next tower our thing is good, so it will dissipate through that tower body. Okay, through that tower body to ground. Okay, or just in case the other tower also has got the same rocky soil, we have to also install lightning arrestor here, and then in the next tower hopefully it is good soil. If it's good soil, then it will get earthed. Okay, for the worst case, obviously our circuit breakers are there in the stations to trip the line in case of any worst condition. Okay, this is it. Thanks.